We know the derivative of the exponential function y equals e to the x. This was one of the first derivative rules that we talked about way back in 3.3. We know that the derivative of y equals e to the x is y prime equals e to the x. It's a pretty cool derivative rule. But this is not the only exponential function that we'll see. What can change here is this base. The base doesn't necessarily have to be that constant e. It could be any number. It could be y equals 2 to the x or y equals 10 to the x. So we want to say, well, what about derivatives of those types of functions? So if we have y equals b to the x, where here b represents any positive number, then y prime is b to the x, so my derivative is b to the x, times this natural log of b. So hopefully this feels really familiar to this derivative of y equals e to the x. And actually what's very cool is that this exponential function, y equals e to the x, follows this derivative rule. It's logically consistent. And I think I'm going to show that here just because it's pretty cool. I think it's neat to look at. So if we're working with y equals e to the x, here the base of my power, b, is this constant e. So, okay, what does my derivative say according to this theorem? It says the derivative should look like, first of all, y prime equals b to the x. So y prime, here's my b. Remember, b in this case is e. E to the x times, what else do I have? Well, I've got natural log of b. So natural log of e, because e was the base of my exponential function. And now I can look at this piece right there and say, well, natural log of e, that's just 1. This is really e to the x times 1, or just e to the x. So hey, we get the same derivative of e to the x if we use this formula here, or if we just use, well, we know that the derivative of e to the x is e to the x, the shortcut. We can also extend the chain rule here. You may have noticed this in section 3.7, but if we're working with an exponential function, y equals e to the u of x. So here, what's different is that my power is going to be something more complicated than x. So it might be x squared, it might be x cubed plus 1, it could be a trig function, it could be all sorts of things. But if I have y equals e to the u of x power, then the derivative is going to be mostly the same. Y prime equals e to the u of x power, so we see that that part's exactly the same. But remember, the chain rule says we just have to multiply by the derivative of that inside part. Here in this case, the inside part is my power, so my derivative is u prime. I think we did one of these way back in section 3.7, so you may have done some homework problems like this. You may have noticed it, but if you didn't, that's okay, because now we have this formula that kind of speeds up the process of using the chain rule. You can still continue to use the chain rule, or you can use this shortcut from now on. I don't really mind. I do think, however, that the way that this is written is a little bit confusing. More often than not, I will write this as u prime times e to the u. All I'm doing is taking this derivative and bumping that up to the front here, and I think that just makes it easier to see that the derivative, that u prime, is a multiple of e to the u, rather than trying to decide what's a multiple, what's in the power. It can be a little bit tricky if it's not written clearly. So I think when we write it as u prime times e to the u, it's just a little bit easier for the reader to understand. So let's look at some examples here. First up, I've got f of x equals 8 to the x. So you'll want to make sure that you notice, first of all, hey, I have this exponential function, but check out the base. The base is 8 here. The base is different than e. So, okay, I'm going to be following this derivative rule. Right here I have y equals b to the x, where my b is equal to 8. So even if you need to make a note to yourself, say, hey, b is equal to 8. So when I take my derivative, f prime of x, what will I have? Well, I'll have b to the x, so that part stays exactly the same. And this is sort of acting kind of like e to the x. We just have this one extra step here. So we said that that part's going to stay exactly the same. I'll still have 8 to the x power, but I said, well, we just have this extra part, and that's where this part is coming from, this natural log of b. So I just need to multiply this by natural log of whatever my base was. In this case, my base was 8. So I'm going to multiply that by natural log of 8. And there is my derivative. I can't really simplify that any further. I think that's written as clearly as it possibly can be. So there's my derivative. I think it's a very cool rule. I think it, hopefully, you can see the similarities between the exponential, kind of the special exponential y equals e to the x, and the general exponential derivative y equals b to the x. Part B, I have y equals 6 times 4 to the x squared power. So this one's a little bit tricky for a couple of reasons. First, you may notice this constant multiple of a 6. And this part right here is actually not the most difficult part. It looks like it's going to impact our problem, but remember that this is just a constant multiple, which means when I go to take my derivative, that 6, that constant multiple, just comes down to my next step. So that 6 actually isn't going to play a big part in my derivative. What will play a big part here is this 4 to the x squared power. So 4 to the x squared, I say, well, 4 to the x squared, there's a few different ways I can think about this. First, I can say, well, this is 4 to the x, so hopefully I'm thinking about y equals b to the x. It looks something like that, but not quite, right? Look at the power. Look at the power right here. It's x squared. It's not just x. So if it's x squared, I actually have a chain rule here. So you may want to, off to the side, and perhaps I just jumped in a little bit too quickly here, you may want to, off to the side, say, all right, I think u should be x squared, which means that u prime is 2x. So if I rewrite this expression over here in terms of u, let's just rewrite it in terms of u. I'm not taking the derivative here. Y is equal to 6 times 4 to the u power. So y is equal to 6 times 4 to the u. Y prime, we said first of all this 6 right here, that constant multiple, not going to be a big problem. We just multiply our derivative by 6. So that 6 is just coming down to the next step. It's just tagging along. And now we say, okay, what does this part look like? Derivative of 4 to the u. Well, the derivative of 4 to the u, that's going to act like the derivative of b to the x. So the derivative of 4 to the u will be 4 to the u, that part is this piece right here, it's b to the x, times natural log of b, so times natural log of 4 here. But remember, we're doing a chain rule right here. We're doing a chain rule. So at the end of all of this, I need to remember to multiply by my u prime. I need to multiply by this guy right here. At this point, I think we're about as set as we're going to be with our derivative. We just need to take our u and our u prime and plug those into our derivative that we found here. So y prime is equal to 6 times 4 to the u. We said u was x squared, times natural log of 4, times u prime. U prime we said was 2x. So u prime is 2x. You could leave your answer like that, but to be honest, for me, this is kind of already bothering me. Just looking at it is bothering me a little bit. I think I can simplify that. I would say, hey, let's multiply the 6 and the 2x because those are two monomials. I can't do anything with 4 to the x squared because that's an exponential function. I can't do anything with natural log of 4. That's a logarithm. You could get a decimal approximation, I suppose, but I would rather just leave that as natural log of 4. But I can multiply 6 and 2x, And when I do that, I'll have 12x times 4 to the x squared power times natural log of 4. Here is my derivative. So 12x times 4 to the x squared power times natural log of 4. One more example for exponential functions. I have g of x equals e to the sine of x power. I'm going to do this problem two different ways. The first way I'm going to use the chain rule, and then the second way I'll actually show how to use this shortcut right here that I mentioned earlier. So if I'm using the chain rule, I need to decide on an inside function, and that inside function is always going to be your power. So u is going to be sine of x. If I have u, I need to find u prime. Derivative of sine of x we know is cosine of x. So let's rewrite our function in terms of u. So g of x is equal to e to the u. When I take my derivative, g prime of x, I know that's e to the u, but I'm doing the chain rule, so I need to multiply by u prime every single time. And I said earlier, I don't really like writing it like that. I think it's just a little bit harder to read. I would rather write that as u prime times e to the u. It doesn't really matter if you do. I think it's just a little bit easier to read. And then we'll take our u and our u prime, and hey, we'll just plug that back in. So g prime of x is equal to cosine of x times e to the u was sine of x. Hey, there we go. There is our derivative. Now, if you wanted to take a slightly different approach, if you wanted to use that shortcut, we said up there, we said if you're working with y equals e to the u, we said u of x, but I'm just going to shorten it and say u here. Then y prime is u prime times e to the u power. So here I have y equals e to the sine of x power, which means that y prime is going to be u prime. That's the derivative of my power, so the derivative of sine of x is cosine of x, times e to the u. U, we said, was sine of x. That's just whatever my power is right here. So e to the sine of x power, and hey, look at this. I got exactly the same derivative both ways. I have cosine of x times e to the sine of x power. So it doesn't really matter which way you end up deciding to use. My recommendation when you're starting off these problems is to practice using the chain rule. I would kind of fall back on that chain rule because I think that gives you a really nice intuitive understanding as to where this shortcut comes from, so that when you do feel more comfortable with these problems, we know where the shortcut comes from, we know why it works the way it does, and that'll make you more successful in applying that shortcut.